Hello everybody, and welcome to the video series about exploiting structure in deep learning. My name is Herke van Hoof, and I'm assistant professor at the University of Amsterdam and scientific manager of the Delta Lab. Let me first introduce our lab. The Delta Lab is a collaboration between the Robert Bosch GmbH and the University of Amsterdam. At the Delta Lab, we do fundamental research in deep learning, with applications to automotive and computer vision. In our lab, 10 researchers work on a variety of topics, such as reliable and robust deep learning and deep learning from multimodal or multi-view data. For today's video, I want to focus on efficient deep learning, especially on learning when data is limited. There have been many success stories in deep learning, many of which you might have seen or will see in another video series in this course. For example, you might have seen stories in the news regarding the success of Google DeepMind's AlphaGo system, have experienced increase in quality of automatic translation services, and seen how services such as face or object recognition can now be used in consumer products and industry. These breakthroughs have been enabled by large datasets. ImageNet is used to learn image recognition and consists of more than 1 million labeled images. Modern reinforcement learning methods are trained with up to 10 billion samples. That is 40 times higher than fits on this comparison chart. This is a problem for many AI systems in practice. Even if many data points, such as images, are available, are they all labeled? And do they cover even rare cases sufficiently? We can contrast this to classical AI systems for planning or reasoning. These systems were completely defined by experts, so did not need any data. However, they were limited by the expert's knowledge and could not adapt to quirks in any particular application. On the other hand, deep learning systems using the end-to-end paradigm are strongly data-driven and hardly depend on expert knowledge. This makes them very adaptive to the task at hand, but only if sufficient data is available. We can understand these systems as white box and black box systems, based on in how far we have control over what is going on inside. However, we might not want to go for one of these extremes, but rather try to go for the best of both worlds. Perhaps we can use the expert knowledge to make the learning task easier, but still use a machine learning system to be able to adapt to patterns in the data. To give some examples, it would be hard for an expert to exactly specify the optimal way to control traffic signals, or how to track and detect objects in an image or video stream. However, we can easily determine whether certain transformations, such as scaling of the input, should have an effect on these decisions. In the case studies, we will investigate how such knowledge can be built into the training process to increase performance. As one other example of research done in the Delta Lab, we can take a look at a hybrid inference system to figure out one's own position based on noisy measurements. Here, we will compare several approaches as the dataset size increases on the horizontal axis and the position error is plotted on the vertical axis. Let's first look at the purple line, which represents that the position is determined using expert knowledge alone. However, if that knowledge is not perfect, the resulting output is not optimal. So, we see that the purple line has a higher error than the optimal solution, shown in yellow. Alternatively, we approach this task in a purely data-driven way. This is plotted with the red line. We see that this can work very well with large data sets, but for small data sets, it performs very poorly. Yet the third approach is to combine expert knowledge and a learning approach into a hybrid method, plotted in black. We see that this always works at least as well as either other method, whether we are in the big data or the small data regime. To summarize, deep learning works extremely well with large data sets. When little data is available, making good use of expert knowledge is essential to retaining good performance. This makes methods that combine expert insights with data-driven techniques very promising. Thanks for your attention, and I encourage you to take a look at our case studies for more details.